हेलो एवरीवन। नेक्स्ट जो हमारा टॉपिक है वो है रिमान फंक्शनल इक्वेशन सेकंड। प्रीवियस लेक्चर में हमने किया था रिमान फंक्शनल इक्वेशन फर्स्ट। नाउ दिस इज अवर सेकंड इक्वेशन. वी हैव टू प्रूव दिस रिमान जीटा फंक्शन दैट इज जीएस इज इक्वल टू 2 raised to power s into pi raised to power s minus 1 sin pi s by 2 gamma of 1 minus s into Riemann zeta function of 1 minus s. This is we have to prove. Now proof is, as we already prove Riemann functional equation first, which is that is this expression is unchanged if we replace s by 1 minus s. This is our Riemann functional equation first. Now multiply equation first. This is our equation first, Riemann equation first. Now multiply this equation by gamma s plus 1 divided by 2. Then this equation will become pi raised to power s by 2 gamma of s. Now we are multiply with gamma of s plus 1 by 2 into g of s. This is our pi raised to power minus 1 minus s by 2 gamma of 1 minus s by 2 gamma of s plus 1 by 2 and g of 1 minus s. This is our equation number second after multiplying 1 with the gamma of s plus 1 by 2. Now consider the property of gamma function. As we know, already proved this property of gamma function, that is gamma of 1 minus s into gamma of s is equal to pi upon sine pi s. Actually we have to find the value of these expression, gamma of s by 2, gamma of s plus 1 by 2. What is the expression for this? We use the gamma properties, gamma function properties, and second we have to find expression for this gamma quantity. So now consider to find the value for this. Now consider the property of gamma function, which is gamma of 1 minus s into gamma of s is equal to pi upon sine pi s. Now replace s by 1 minus s by 2. Then we get this if we replace s by 1 minus s by 2, then this quantity will become gamma of 1 plus s by 2, and this is our gamma of 1 minus s by 2. Now this is pi sine pi s replaced by 1 minus s by 2, and this is our equal to pi sine pi by 2 minus pi s by 2. This is in the first quadrant at the pi by 2. This angle will change, so this is equal to and sine is positive, this is equal to cos pi s by 2. So this is our this will become pi upon cos pi s by 2. This is our equation number star. So for this expression gamma of s by 2, gamma of s plus 1 by 2, for this gamma of 1 minus s and the gamma of 1 plus s by 2, we get the expression pi upon cos pi s by 2. This is our equation number second. Now we have a duplication formula, which is gamma of 2s is equal to 2 raised to power 2s minus 1 divided by under root by gamma of s, gamma of 1 plus s by 2. Now just replace s by s plus 2 in this duplication formula, and then we get this gamma s by 2, gamma of s plus 1 by 2 is equal to under root pi 2 raised to power this is under root 2 pi 1 minus s into gamma s. This is our equation number second, double star. So now we are use star and double star into the equation number second. So finally we get the expression for these both quantity, this one and this one, into star. For this we get the star equation, and for this we get the double star equation. Now we just use star and double star into equation number second. So then we get gamma of raised to power minus s by 2 pi upon 2 raised to power 1 minus s into gamma of s. This is our Riemann zeta function gs is equal to pi raised to power 1 minus 1 minus s by 2 pi of cos pi s by 2 and g of 1 minus s. So this is our g minus 1s, and these all quantity comes into the left hand side, and then finally it become cos pi s by 2 2 raised to power pi s raised to power s. You can solve all these term related to pi into left hand side and then combine the power. So we finally get 2 raised to power 2 pi raised to power s into gamma s and g of s. Now just replace 1 minus s, this quantity 1 minus s by s. So we get g of s cos pi 1 minus s by 2 2 raised to power 2 pi 1 minus s. This is our gamma 1 minus, and this is our g 1 minus s. So this is gs and this is cos pi by 2. Then finally it becomes sin pi s by 2. This quantity will become 2 raised to power s pi raised to power s minus 1. It comes into denominator, so this will become negative, that is s minus 1. This is our gamma 1 minus s and g of 1 minus s. This is our equation number 2, Riemann functional equation 2. So our last topic of the unit 1 is Runge's theorem. Before to prove this theorem, we have to prove one proposition, one lemma, and then we have to prove this theorem. So firstly we see the proposition. The statement of the proposition is, let K be a compact subset of the region G, then there exist a straight line segments gamma 1, gamma 2, gamma 3, gamma n in the complement of K, that is G minus K, such that for every function f in Hg, here Hg represent holomorphic function on the region G. So for every function f in Hg, fz can be written as like this, that is summation k is equal to 1 to infinity 1 upon 2 pi at the integration along the line segment gamma k fw w minus z into gz for all z in K. The line segment form a finite number of closed polygons. Means if we combine these line segment, then they form a closed polygon. Now this is our region G, say, and this inside region is our K region. Then we have to divide this whole region into a grid of horizontal and vertical lines. So suppose that the region K enlarge little by assuming that this K is equal to interior of K then closure, and let delta be a quantity which lies between 0 and the upper bound is for this delta is 1 by 2 distance of K. This is K our compact set and the complement of G with respect to complex number system, that is C, not extended, just the complex number set of complex numbers C minus G, complement of G in C. So delta is a quantity which lies between 0 and 1 by 2 distance of K and C minus J. Now construct a grid of horizontal and vertical line in the plane. This is our region G, this is our complex plane, and this is K. Now we have to divide this whole plane into a grid of horizontal lines and vertical lines, such that the conjunctive lines are less than a distance of del apart. मीन्स दो कंजक्टिव लाइन आपकी हॉरिजॉन्टल या वर्टिकल लाइन से, दो कंजक्टिव लाइन अगर आप लें तो उनके बीच का जो डिस्टेंस है वो हमारा डेल्टा से स्मॉलर रहना चाहिए, और डेल्टा के लिए हमने जो बाउंड्स है वो हमने डिसाइड कर लिया कि डेल्टा क्या होगा. नाउ लेट रेक्टेंगल इंटरसेक्टिंग के बी द R1, R2, Rm, and let del Rj be the boundary of the rectangle Rj for all j less than equal greater than equal to 1 less than equal to m. Suppose Rj and Ri and Rj have the common side, and let sigma j and sigma I be the line segment in del Ri and del j respectively, such that this intersection will be either sigma j or sigma k. What we are doing, we have this complex plane, this is our region G, and this is any compact set K. We're just dividing this complex plane into a horizontal and vertical lines, this type of grid. Now we say this is the rectangle R1. जो भी रेक्टेंगल हमारे किसको K को इंटरसेक्ट कर रहे हैं उनको हमने नाम दे दिया R1, R2 एंड R3, लाइक दिस ट्रायंगल. तो इनको हमने क्या नाम दे दिया R1, R2, R3 एंड Rn. जैसे ये R1 मान लीजिए, ये R2, एंड इस तरह से हमारी ये रेक्टेंगल बनेंगी. जैसे हम प्लेन को डिवाइड करेंगे लाइक दिस, मान लीजिए यहाँ पे कोई आपका सेट है K, तो ये जो रेक्टेंगल हैं हमारी इनको हमने नाम दे दिया दिस इज R1, दिस इज R2 जो K को इंटरसेक्ट कर रहे हैं, दिस इज R3, R4, एंड जो बाउंड्री हैं ये हैं, इनको हम डिनोट कर रहे हैं डेल्टा Rj से. अब जो सिग्मा I और सिग्मा J हैं वो सिग्मा I मान लीजिए ये आपकी ith ट्रायंगल है, ये आपकी jth ट्रायंगल है, बाउंड्री आपकी हो जाएगी del ri and del rj respectively. Then we always taking the anti-clockwise direction. This is the direction, and for this is the direction. Means at this common region between the triangle, this quantity is sigma I, and for this is sigma j. This is the boundary region, and we say this is sigma I and this sigma j, and they are in opposite direction. So suppose Ri and Rj have the common side, and let sigma and sigma j be the line segment on the boundary of del ri and del rj. This is the boundary of our ith rectangle and jth rectangle respectively, such that this intersection, if we are taking the intersection of these two, then what will be the common? This thing will be common, and for this for Ri we say this is sigma, and for Rj we say this is sigma j. So we can say this intersection of these two quantity, we can say either sigma I or sigma j, because sigma I and sigma j are nothing but they are equal but in opposite sign. So this intersection will be sigma j, sigma I, or we can say sigma j. According to the direction given del ri and del rj, the sigma I and sigma j are directed in the opposite direction. So if psi is any continuous function on this line segment sigma I, or we can say sigma j, then we have this integration of this continuous function along the line segment sigma j is opposite to the, because rj and this is sigma j and sigma I are in opposite direction. So we can write this integration along sigma j of psi is equal to negative of the sigma I. So this implies this integration along sigma I psi plus integration along sigma j plus psi is equal to 0. Now suppose that this gamma 1, gamma 2 and gamma n, that is line segment, are these directed line segment that constitute a side of exactly one of the rj. Means हर जो लाइन सेगमेंट है वो किसी न किसी आरजे की एक साइड होगी, बट एग्जैक्टली वन की होगी. ऐसा नहीं है कि एक लाइन सेगमेंट हम उसको R1 की बोल रहे हैं, R2 की भी बोल रहे हैं, तो वो एग्जैक्टली वन आरजे की एक साइड होगी जो हमारी लाइन सेगमेंट्स हैं. तो हम यहाँ पे समेशन अप्लाई कर सकते हैं. सो देन समेशन k इज इक्वल टू 1 to n सिग्मा गामा k इंटू साई इज इक्वल टू समेशन j इज इक्वल टू 1 to n बाउंड्री ऑफ डेल rj is equal to psi, because any sigma k, this is gamma k, sorry, any sigma gamma k is the boundary of exactly one rj. Means suppose this gamma 1 is the boundary of r2, gamma 3 is boundary of r5, like this. Then we are taking summation, then we get all the terms. So this is our equation number 2. Now we claim that if gamma k in g minus k, if one of the gamma k intersect k. Further, if z belongs to k and is not the boundary, and it is not on the boundary, means we have to consider a point in k which is not in the boundary of any rj. means जो k है हमारा वो किसी भी ट्रायंगल की बाउंड्री पे नहीं होगा. इस तरह से हमने z कंसिडर करना है. तो उस z को हम क्या लिख सकते हैं, दिस for a continuous function psi w is equal to 1 upon 2 pi iota fw upon w minus z is a continuous on the union of the boundary of each ri for a holomorphic function in G. Thus from first we just put the value of sigma psi w in equation number first, then we get sigma j is equal to 1 to m 1 upon 2 pi iota integration along the boundary of rj is equal to fw w minus z is equal to dw, or we can say summation k is equal to 1 to m 1 upon 2 pi iota integration along the line segment gamma k, and this is our fw w minus z into dw. But z belong to the interior of the exactly on rj. कि अगर पॉइंट हम z कोई भी पॉइंट है k का और वो बाउंड्री पे नहीं है, तो मीन्स इट बिलोंग्स टू द any rectangle rj. If z doesn't belongs to rj, then this quantity if Rz doesn't belongs to Rj for any j, then this quantity belongs to this quantity, this integration with multiply 2 pi 1 upon 2 pi iota is equal to 0 and by Cauchy theorem, because in this case this quantity will become analytic, and if it is analytic then by Cauchy theorem this integration will be 0. And if z belongs to Rj, then by Cauchy integral formula we can say fz is equal to 1 upon 2 pi iota integration along the boundary of Rj fw w minus z into dw for a holomorphic function in G. So finally for at the place of this quantity we can write fz. So fz is equal to 1 upon 2 pi iota summation k is equal to 1 to m along the line segment sigma gamma k fw w minus z into dw, that is we have to prove. So this is our proposition number first. Now we are left with only lemma that is used in the proof of Runge's theorem. Then we see the proof. Only one lecture is left for the unit first. So